Hi viewers, welcome to my channel. This is Anthony Vijay. In this video, I am going to explain about breadth first search from Graph Traversal. First of all, we will be going to see about the introduction part of breadth first search. So the final outcome of the breadth first search is spanning tree. The spanning tree is a graph without any loops. Okay, this is called the spanning tree. So usually breadth first search follows a queue data structure. So let's have a look about the following steps involved in implementation of breadth first search traversal. The first step, we are going to assign the queue size for the particular traversal that depends upon the number of vertices available in the graph. So for example, in the particular example, we have 7 vertices, means we supposed to have the queue size is 7. So it is purely depends upon the number of vertices. Okay. In the next step, we are randomly going to start the vertex point. Okay, that is the starting point will be a random point. Okay. So once we have visited the particular vertex, after that we have to insert the particular vertex into the queue. In the next step, we are going to find the adjacent vertices of the particular vertex. The adjacent must be non-visited one. Okay, so that particular vertex is supposed to be inserted into the particular queue. Before inserting into the particular queue, we have to remove the already the friendmost element in the particular queue. Okay, this is the process we have to repeat. And at one point of time, we don't have any new vertex to be visited. At that time, we have to remove the particular friendmost vertex from the particular queue. So this particular process to be repeated until the particular queue is empty. So at the final point of time, we have to remove the unused edges from the graph. Finally, we get the spanning tree. So let's have this particular explanation with the help of diagrammatic representation. Let's have a look about it. So let's have a look here. Here we have 7 vertices from A to G. Totally we have 7 vertices. So the queue size must be 7 only. So first of all, I am going to take the starting vertex as A. It's supposed to be random, so anyone can start from anywhere. Okay. So once we are visited A, so we have to insert the particular vertex into the queue. So in the next step, we have to find the adjacent vertices of the particular A. So for A, the adjacent for A is B and E and D. So adjacent means whatever vertices are connected with directly connected with the particular vertex. So for A, the adjacent vertices are B, E and D. So the next step, so we have to insert B, E, D directly. Before inserting the particular into the queue, so we have to remove the friendmost vertex in the queue. So in this queue, the friendmost vertex is A only. So we have to remove the A, and one free space will be there. After that, we have to add like this. D is the adjacent part, and E also adjacent, and B also adjacent. So in DFS, in the stack, we have inserted one vertex at a time, but in queue we are inserting all the adjacent vertices at the same time. This is the difference between DFS as well as BFS. So this process to be repeated. So next I am going to take the again the friendmost element. So here the friendmost element is D. So from D we have to find the adjacent vertices. So here the adjacent vertices is already it is visited. See, the adjacent vertices of D is what? E and A. So it is already in green in color. Green in color means what? It is already visited. So there is no other new unvisited vertices are there, so that we can directly remove this second element, that is called right now the friendmost element is D only. So we are removing D here. So see, the D part is free now. Now we have E and B only. Now I am going to take E. So from E, I am having 2 adjacent vertices. One is C, the other one is F. So I am going to insert after B. Before inserting, I want to remove the vertex E. Okay. So right now after B, I am inserting C and F. So C and F is inserted after B. C, the E is removed here. After that, I am going to take B here. So after B, there is no other adjacent vertices. So that if there is no new unvisited vertices are there now, so we have to remove this particular Q. Right now we have C and F. So in this C and F, so for adjacent for C is what? G. So we have to insert this G after F, so that before inserting G after F, we have to remove the C. Okay, this is so finally we have F and G. So now again we have to check with F. So after F, there is no new unvisited vertices are there, so that we have to directly remove this F. After that, only one vertex is there, that is G. So after G, no other new unvisited vertices are there, so that we are removing. So finally Q is empty. So after the Q is empty, we are going to remove the unused edges. So here I am marking out the unused edges. So we are going to not consider this. So let's have a look about the spanning tree. So here B to C, that link is unused. C, there is no link. After that C to F is not there. See this in the final spanning tree, we are removing the unused edges. So see here, there is no link between B and C. See in this previous one, there is no in the link between B and C, and C and F. C and F, no link is there, and F and G, no link. F and G, no link, and D and E is no links. Okay, so this is the spanning tree part. So this is the final outcome of our breadth first search. Okay.
Please like and subscribe to my channel and press the bell icon for regular updates. Thank you very much for watching.